Hello everyone, welcome to this short review on organic chemistry. So in this video we will tackle the different organic molecules, its functional groups or the functional groups um, that we will encounter in biochemistry. So first of all, what is organic chemistry? So we know that for those who had sufficient background in chemistry, organic chemistry is a branch of chemistry that deals with carbon-containing compounds. So there are lots of carbon-containing compounds, and in this presentation, we will see the general or the overview of the organic chemistry. Organic chemistry is a very vast uh, topic. We will only cover the basic or the foundation of organic chemistry. Okay? One of the groups of organic compounds is called the alkanes. Alkanes are organic molecules that are or that contain carbon and hydrogens. So alkanes, take note that they only contain carbon and hydrogen. So that's why alkanes are called hydrocarbons. Okay? The general formula of alkane is CnH2n plus 2, where N is any positive integer. Alkane is considered to be saturated. Okay, what it means by saturated? The carbons in alkane are single bonded. For example, here you have 3 carbon atoms connected to one another by a single bond. So remember that carbon atom is capable of forming 4 bonds. So alkanes are hydrocarbons, contain only carbon and hydrogen. So this carbon has 3 hydrogens on it. Okay, so we will put 3 hydrogens to satisfy the 4 bonds. In this middle carbon, we put only 2 hydrogens because this carbon has already 4 bonds. So likewise in this carbon, we will also put 3 hydrogens. Okay, so what I have just written is the expanded molecular structure of this particular alkane. Now, the formula of this is, or the molecular formula of this would be following our general formula, which is CnH2n plus 2, where n is any possible integer, but basically the n is equal to the number of carbon in the chain. So how many carbons in the chain? There are 3. So the formula can be C3H 3 carbons times 2, so that's 6 plus 2, that's 8. C3H8, that's the formula of this molecule. So if we count 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this now is the expanded molecular structure, and this is the molecular formula of this particular alkane that I have drawn. All right. Now, to name alkanes, we just have to determine the number of carbon atoms in a chain. Okay, for example, if there is one carbon atom only, the root is called met. Okay? And if there are two carbons, the root is et, and so on and so forth. And then from this root, we will add letters ane from the word alkane. So if there's only one carbon, the name becomes methane. Okay, so this becomes, let's write methane. Okay, for one carbon. Okay, remember that carbon must have 4 bonds. Okay, so let's put here 4 bonds for methane. Okay, so this is the expanded molecular formula. When the structure of the formula of methane is CH4. Okay. Now, if you have five carbons, so you just add here pent. The root is pent plus, let's put ane. So that becomes pentane. All right. So if this is the carbon, 1, 2, 3, 4, 5. Okay. Then each carbon must have the corresponding hydrogen. Okay. Take note that the terminal carbons, the beginning and the end, must have always 3 hydrogen atoms, while those in the middle carbons, we put only 2 hydrogens in each. Okay, without counting the number of hydrogen, we must be able to determine the molecular formula of pentane following the general formula, which is CnH2n plus 2. So how many carbon atoms? There are 5. So let's put here C5, and then the number of carbon atoms is 5 times 2 is 10 plus 2, so 12. So the molecular formula of pentane is C5H12. So you just have to apply the following principle in each of this methane group or alkane group, from methane to decane. Okay, decane has 10 carbon atoms, although there are hydrocarbons that are even longer than decane. There are what we call isomers. When we say isomers, they are compounds that have different arrangement of atoms, but the same molecular formula. So we have constitutional or structural isomers. They have the same molecular formula but different arrangement bonded to atom. For example, I have here, let's say 1, 2, 3, 4. So this is butane. Okay, this is butane, and then of course you put the hydrogen atoms there. I will not put the hydrogen. I'll just put here bonds. Well, you know that these bonds, well, I put hydrogen, one hydrogen. Anyway, the bonds correspond to the bond or the line corresponds to this hydrogen atom. Okay, so here you have a linear butane, or simply if it is linear, we put here N butane. Okay, N before the word butane because that is a linear. Now, another possible arrangement is, okay, well, by the way, what is the formula, molecular formula of butane? So you just write here C4H10. Okay, so 3 plus 3, 6, 2, and 2, that's 10. Okay, then we could rearrange this molecule into this. Okay, I will now put the other carbon below. All right, and I can put the hydrogens on each of the carbons. So 1, 2, 3. Then here same 1, 2, 3. Here 1, 2, 3. Okay. On this carbon, I can only put one hydrogen because this carbon has already 4 bonds. Okay. So still, if you will count the number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So as you notice, they have the same molecular formula, C4H10, but the carbon atoms are arranged differently. They are called structural isomers. Okay, the arrangement of atoms differ. Since they are different compound, they exhibit different chemical properties. Now next is alkene. Alkenes, take note that it has an E instead of A for alkane. Alkenes have, or hydrocarbons that have at least one carbon-to-carbon double bond. Okay? Alkenes are called unsaturated. Unsaturated meaning the carbon atoms are not yet saturated with hydrogen atoms. Okay? So the general formula of alkene is CnH2n. Remember, in alkane, there must be CnH2n plus 2. But for alkene, okay, CnH2n only. And alkene ends with ENE. For alkane, it ends with ANE. Alright? For alkene, the simplest molecule, there must be 2 carbon atoms. Alright? So, for example, here, a carbon-to-carbon double bond. Okay, this is the simplest alkene. Okay? You just have to apply the root. Okay, the root word for the number of carbon atoms. For 2 carbon atoms, the root word is et. Okay, and since alkene ends with ENE, so we add ENE from the word, from our root, so that becomes ethene. Okay, ethene. Ethene is a carbon-to-carbon double bond, and each carbon has 2 hydrogens. Okay, has 2 hydrogens. Still, the carbon atoms have 4 bonds. Okay, if there are 3 carbon atoms, the root is pro. Okay, pro, and then if the double bond is here, all right, so we just prop, the root is prop, then we add ENE, then that's called propene. Okay, then we put the corresponding number of hydrogen. Here there must be 3 hydrogens. Take note always that carbon must have 4 bonds. So if we put here 3 hydrogens, there will be 1, 2, 3, 4 bonds. Okay, this carbon in the middle has already 3 bonds, 1, 2, 3. That's why I can put 1 more hydrogen. And then on the last carbon, okay, on this carbon rather, not necessarily last, there are already 2 bonds, so I can put 2 more hydrogen. So that's how you write the structure of propene. This is the expanded formula, molecular formula of propene. Just like alkanes, alkenes also exhibit isomerism. So it says here, alkenes may exist as geometric or cis-trans isomers. Okay, so the cis-trans isomers, they are called geometric isomers, which differ in the orientation of the groups attached to the double bond. Okay, so the geometric isomers, they have different physical properties, although the formula of the remember isomers, they have the same, no, same molecular formula, but different arrangement, okay, of atoms. They have different physical properties. So example, this is these are two examples of these are two examples of geometric or cis and trans isomer. Okay, one is called cis-2-butene, the other one is trans-2-butene. What is the difference between the two? Well, structurally they are different, but the molecular formula, their molecular formulas are the same. Butene, but, remember the root is but, and then since there's a double bond, we add ene. Okay, and then as you notice here, the double bond is on the second carbon. This is being the first, and then the second carbon, okay, the third carbon, and the fourth carbon. Now you notice that this CH3, we call this methyl groups. Okay, you notice that the methyl groups are on the same side. Okay, same side of the plane. That's why the designation is cis. Okay, as you can see also, the hydrogen atoms are on the same side. So the methyl groups or the substituents are at the same side, the hydrogen atoms are at the same side. Okay, we call this geometric isomer cis. All right, this happens only in molecules that have double bonds. Okay, the opposite, as you notice, when the methyl groups, okay, are at the opposite side, or also you can see that the hydrogen atoms are at the opposite side, you call that trans. Okay, take note that the hydrogen atoms must be opposite side. The hydrogen atoms, take note, the hydrogen atoms that are connected on each of the carbon with double bond. Okay, although there are hydrogen atoms here in the CH3, but they are not bonded in the double bond. So our consideration is the hydrogen atom or atoms that are connected on the carbons that are double bond. Okay, so when we represent these two molecules using line formula, okay, these are line formulas. This is how we write them. This end here corresponds to one carbon. This corresponds to a carbon. The angle, that's a carbon also, and this angle here corresponds to a carbon, and this end here also corresponds to a carbon. The double bond is in between the second, okay, second, and the third carbon. In a line formula, we don't need to write the hydrogen atoms anymore. But it is understood that on this carbon, there are 3 hydrogens. Likewise, there are also 3 hydrogens here. Okay, But on these carbons, on the middle, on the second, on the third, there are only two hydrogen atoms. Oh, there's one. Okay, sorry. There's one on there's one on each. Okay, carbon. Okay, as you notice, even though they have the same molecular formula, okay, their properties differ. One boils at a higher temperature than the other. Okay. Now next is alkyne. Alkynes are hydrocarbons that contain at least one triple bond. Okay, let's recall alkane, single bond. Carbon to carbon is single bond or has single bond. Alkene, carbon to carbon, has one double bond or at least one double bond. And then alkynes, now take note, it is Y and E. Okay, it has a triple bond. The general formula is CnH2n minus 2. Okay, they are also unsaturated because they have more than one bond. You just have to name alkyne. It says here, same way you apply the principle as you are naming alkenes. You just have to use or to add the suffix y and e to the root word. Say for example, the simplest alkyne has two carbon atoms. You cannot have an alkyne that's only one carbon. For alkane, it's possible, the methane. Okay, for alkene, there must be two carbons. For alkyne, of course, two carbon also. So here, the carbon atoms have already three bonds. Okay, so therefore, we can only put one hydrogen. So the formula, the molecular formula is C2H2. Okay, following the formula of CnH2n. It must have been C, okay, C2. I said earlier, the n is the number of carbon atoms. So if we multiply 2 times 2 is 4, but we subtract 2, so that's why C2H2. Okay? There are many organic compounds that contain not only carbon and hydrogens. There can be atoms such as oxygen, nitrogen, and the halogens bonded to the carbon. So those molecules or those organic compounds can be categorized based on the functional groups. Okay, so functional groups in a compound determine both its physical and chemical reactivity. So what dictates the property, the chemical reactivity of that organic compound is dependent on the functional group or functional groups it contains. And it says here functional groups define the region of high and low electron density in the compound, thus determining its reactivity. In the following slides, we will see the different functional groups that can be present in organic molecules. So these functional groups, we have to really look on each of these functional groups because you will encounter many functional groups in biochemistry. Okay, these are the functional groups in organic compounds also. And then we have We have alkane, that's considered as functional group. Okay, alkene, sorry, the carbon to carbon double bond. Okay, so we have learned already how to name alkene. Then alkyne, those that have triple bonds. Okay, and then notice that in this particular compound, there's additional atom, and that is oxygen. Aside from carbon and hydrogen, there is an addition of oxygen. So we call the compound alcohol. Okay, alcohol ends with all. So you just have to add all from its uh, parent name. Okay, one carbon, remember methane. So you just have from the word methane, okay, you drop the letter E and then replace it with all, okay, for methanol. So same principle applies as the number of carbon increases. So the basic thing is you have to memorize the root word from 1 carbon to 10 carbon. Met for 1, et for 2, prop for 3, and so on. For alcohol, this functional group is called hydroxyl group. Okay, OH. We call this hydroxyl group. Okay, hydroxyl group is a neutral compound. It's not charged, unlike the hydroxide that we have seen. Hydroxide is negatively charged. Next is haloalkane. Okay, in a haloalkane, the attachment or the other atom that is attached is called halogen, represented by the X. Halogens are the elements that belong to group number 7. The fluorine, okay, so the halogen may be fluorine, chlorine, bromine, or iodine. So we call them haloalkane. So example, when chlorine atom is connected to this carbon, there's only one carbon, so you call that chloromethane. Okay? Or methyl chloride. Methyl chloride, the one in the parentheses, it's the common name. Okay. Next is amine. All right. For amine, there is the presence of nitrogen. Okay, and there must be 2 hydrogens here. Okay, amine is basic. Okay, amine is basic due to the presence of lone pair. Look at the 2 dots there. Those are the lone pair electron. So when an amine is added to a hydrocarbon, okay, you call that, let's say in this example, there are 2 carbons, okay, so that's ethane, but it ends with amine, so you say ethanamine. That's the systematic name, ethanamine. Ethane, 2 carbons, but it ends with amine, so you say ethanamine. The common name is ethylamine. Ethyl, that means 2 carbon atom also, ethyl. Then next we have aldehyde. Okay, aldehyde ends with al. Okay, so you just have to include, or you just have to put al as a suffix from the root word. Remember, the root stands for the number of carbon atoms in a molecule. So here in this example, there are 2 carbon atoms, okay, and the root word is ethan, okay, or ethane, okay. Then we just have to add al at the end as a suffix. So the name, the scientific name or the IUPAC name is called ethanol. Okay. Um, in addition to that, an aldehyde, the functional group is C, doubly bonded to oxygen. Okay, and there's one hydrogen, as you notice in this example. Okay, this carbonyl group, we call this carbonyl. In aldehyde, the carbonyl group must be at the terminal. When you say terminal, at the end, most carbon. Okay, so therefore, this carbonyl group here must be connected to an R. Okay, an R, when you see R in organic compounds, this represents the rest of the molecule. Okay, so for example, for alcohol, the functional group is OH, hydroxyl group. When OH is connected to R, this is the general formula of an alcohol. Okay, so let's write here alcohol. For aldehyde, the carbonyl group, remember, this is the carbonyl group. You always write the carbonyl that is connected to the R, because the carbonyl only does not stand, no? So that must be connected to the rest of the molecule. Okay? So this is the general formula of aldehyde. Although the simplest aldehyde contains only one carbon. Okay, so you can say this carbon that has only one this molecule that has only one carbon can have 2 hydrogens on it. Okay, so this is called metanol. Okay, meta or methane, there's only one carbon. Okay, and then the functional group is the aldehyde itself. Okay, so that's called metanol. So for metanol or for the aldehyde, you just have to determine the presence of carbonyl group at the terminal carbon. The next set of functional groups in organic compounds are the following. We have ketone. The ketone, okay, as shown here, the carbonyl group, remember, always the carbonyl group is the carbon bonded to oxygen. That's a carbonyl group. In ketone, the carbonyl group must be in between 2 carbon atoms. So the general formula could be R, C, double bond O, R. Unlike in aldehyde, the aldehyde, okay, as I wrote earlier, the carbonyl must be at the terminal atom or the end most carbon. Okay, so that's why here the carbon is bonded to hydrogen. But for ketone, the carbon is bonded to another group of molecules. So that must be group of carbon atoms. Okay, so think of it that a ketone, the carbonyl group must be in between 2 R groups or the rest of the molecule. Ketone ends with -one. Okay, so you just have to add this as a suffix in the number of carbon atoms. So the simplest ketone has 3 carbon atoms. You cannot have a ketone with only 2 carbon atoms. The simplest must have 3 carbon atoms. Okay? So here you have 3 carbon atoms. The ketone group is on carbon number 2. So this is 1. Okay, the carbonyl group is the carbon number 2 and then carbon number 3. Okay? The root is prop or propan. Okay? And then the functional group, this is our functional group, remember? The functional group is on carbon number 2. So you say 2-propanone. 2 because the functional group is on carbon number 2. Okay? 2-propanone. And the common name is acetone. The 2-propanone is actually the old systematic way of naming. The new way to name this is propan. Okay, propan, that is the root, and then the functional group is on carbon 2, so you say propan 2-one. Okay, that's how you write the name. This is the newest, okay, way of naming the organic compounds. The next functional group is called carboxylic acid. Carboxylic acid ends with oic acid. Carboxylic acid is generally a weak acid. The general formula of carboxylic acid is C double bond O. This is the carbonyl group. Okay, but on this carbon there's another group of atoms, that's the OH. So all in all, the whole thing is called carboxyl group. Okay, this is the carbonyl plus OH. Okay, the whole thing is carboxylic acid. This hydrogen here is acidic. Carboxylic acid, as I said, is acid. They are generally weak acid. So the simplest carboxylic acid contains only 1 carbon. Okay? This is the simplest carboxylic acid. So carbon must have 4 bonds. So it has already 3 bonds. 1, 2, 3. So we can put 1 more hydrogen. Okay? Since there's only 1 carbon atom, the root is methane. Okay? Methane. Then we will add a suffix oic acid. So we'll write here methane plus oic acid. So that's the simplest. Carboxylic acid has only 1 carbon atom, methanoic acid. So in the example here, there are 2 carbon atoms. So we know that a carbon atom has 2 carbon atom has a root of ethane, then plus oic acid. That's why ethanoic acid, or commonly known as acetic acid. Acetic acid is an acid present in your household vinegar. Next is we have ester. Ester, to form an ester, the hydrogen here in carboxylic acid. Okay, take note, in carboxylic acid, there's hydrogen bonded to the oxygen. But in ester, the hydrogen is replaced by a carbon, by an alkyl group. Okay? The general formula of ester is R, that's the rest of the molecule, carbon to carbon double bond, okay, and then O, and then another R group. Okay, when you encounter this general formula, it means that the molecule is ester. Ester is formed between the reaction of carboxylic acid, okay, take note, carboxylic acid, I write here the general formula of carboxylic acid, plus alcohol. Okay, so next time when you are asked how ester is formed, it's due to the reaction or combination of a carboxylic acid and alcohol. All right. Now next is amide. Then we have amide. Amide is a carbon with double bond and it's connected to a nitrogen atom. As you notice, when amide is named, it ends with amide. So a two carbon atom with amide is called ethanamide. Then we have nitrile, a carbon to carbon triple bond. Let's consider them one by one. So again, let's go back to amine. So as I said, amines are functional group that contains carbon atom. Very important thing that you have to consider in amine is generally amines are basic due to the presence of a nitrogen with a lone pair of electron. So amines, since they are basic, they can accept acid, they can react to acid, or they can participate in acid-base reaction. So again, to name amine, you just add the suffix amine after the root word. Okay, remember, so the root word depend on the number of carbon atom. Okay, so here, example, you have diethylamine because this is a this is an ethyl. Ethyl means two carbons. Okay, ethyl. This is also ethyl. Okay, there are two ethyl groups, so diethyl, and then the functional group is amine. That's why it's called diethylamine. Amine comes in three form. It could be primary amine, secondary amine, and tertiary amine. In primary amine, as you notice, there's only one R group. There's only one alkyl group. Okay? So example is this. Okay? There's only one carbon attached to the nitrogen. That's primary amine. A secondary amine is if there are two carbon atoms bonded to the nitrogen. That's why here there are two R groups. So this is one R, another R group. That's secondary. And then tertiary amine, as you notice, there are three R groups. That means in a nitrogen, there are three carbon atoms. There are three groups of carbon atoms. Okay? Each of them, they have different physical and their reactivity differs. Okay? The primary and secondary amine can form hydrogen bonds. Therefore, they have higher melting point and boiling point. So they could bond very easily to water, for example, or they can form hydrogen bonds with alcohol. That's why it says here they have higher melting point. Okay, tertiary amines cannot form hydrogen bonds. That's why they have lower melting point, they have lower boiling point. Okay, and then amines of low molar mass are fishy smelling, water soluble, and weakly basic. So the reason why they are basic because of the presence of pair of electron on the nitrogen atoms. Now let's go back to aldehydes and ketone. Okay, aldehydes and ketone, as I said earlier, both of them contain carbonyl group, and this is a carbonyl group, C double bond O, and this functional group is polar. Okay, polar because the oxygen atom is electronegative. These are some examples of aldehydes and ketone. As I said, methanol, that's the simplest aldehyde, commonly known as formaldehyde. Okay, it has only one carbon. Okay, bonded to this itself is the functional group of aldehyde. But notice that the carbonyl group is bonded to one hydrogen. That's why this is the simplest aldehyde. Okay, an aldehyde could be connected to this molecule. By the way, this molecule is called a benzene. Okay, benzene ring. Okay, so when you encounter this molecule that is a benzene ring, that's actually made up of 6 carbons with alternating double bond. Okay, it could also be written this way: alternating double bond, if the double bond can be written here or there or here. So these two molecules are the same. Okay, these two molecules are the same, so that's why instead of writing two molecules, since they are the same, some writers, they just put hexagon with circle inside to represent that the double bonds can be anywhere along the or among the 6 carbon atoms. Okay, so the circle inside the ring represents or it tells us that the double bond could be anywhere. Okay, not only on these carbons, all right, but could only be on these 3 carbons here. Okay, so here the examples of ketone, as I said earlier, no, 2-propanon. Okay, 2-propanon uh, must have 3 carbon atoms. By the way, 2-propanon must be this. All right. Okay, and this is the 2-butanon. I just put arrow so that you will not be confused. Okay, 2-butanon, buta 4 carbon atoms. Okay, so you write here, this is the carbon number 1, carbon 2, carbon 3, and carbon 4. Okay, our number, to number the carbon atom, we must indicate the lowest possible numbering in the carbon that has the functional group. Okay, that's why this is designated as second carbon, because this carbon has our functional group, and the rule says the carbon must always have the lowest possible numbering. Okay, so the old way to name this is 2-butanon, but as I said earlier, this must be butan. Butan means 4 carbon atoms, and then the double bond or the carbonyl is on carbon number 2. That's why butan 2-one. And then the propanon, this one, This molecule must be propan 2 propan-2-one. Okay, 1, 2, 3. Propan means 3 carbon atoms. Okay, carboxylic acid, as I said earlier, this is the carboxyl group. Okay, and then when we name carboxylic acid, it ends with oic plus acid or oic acid. Carboxylic acids are weak acids. They react with base, could be strong base or a weak base. So for example here, a metanoic acid, that's the simplest, it's not metanoic acid. This should be ethanoic acid. Okay, ethanoic acid. The labeling is incorrect. Ethanoic acid. This is commonly known as acetic acid. So when ethanoic acid reacts with sodium hydroxide, that's strong base, you form, again this is incorrect, this is ethanoate. Okay, ethanoate. Alright, ethanoate because the oxygen here is negatively charged. Okay, so these are some examples of molecules with carboxylic acid. Metanoic, commonly known as formic acid, there's only one carbon. Okay, here, how many carbons are there? There are 4. 1, 2, 3, 4. That's why buta 4. Okay, butanoic acid. And then here you have a carboxylic acid bonded to benzene ring. I have shown you earlier what is benzene ring. Okay, this is called benzoic acid. Okay, here you have a molecule that has 10 carbon atoms, or by the way, not 10. There must be 18 carbon atoms. Okay, it's a very long molecule. This is actually a fatty acid. It's called fatty acid. It has 16, 17, 18. Okay, 18 carbon atoms, and it's called esteric acid. We will see this when we go to lipids in biochemistry. Okay, ester, as I said earlier, ester is formed when ethanoic acid and an alcohol combine. Okay, the process, the reaction is called esterification. Okay, whenever you encounter ester that is produced from the ethanol, from generally carboxylic acid, okay, carboxylic acid plus alcohol. Okay, that's how you form ester. So here you have ethanoic acid plus methanol. Okay, water is removed. This is water. All right, and then you notice that the product is called methyl ethanoate. This part here is called eta. This is the ethanoate. This portion here is the methyl. The methyl comes from the alcohol. Okay, the ethanoate comes from your carboxylic acid. All right. Okay, these are some molecules that contain ester group. We will see this in many of the ester groups can be found in, can be encountered in lipids or lipid chemistry. Okay, So this is an example of an ester, a triglyceride, all right? And it could undergo saponification, okay? Saponification is the reaction wherein an ester is hydrolyzed in the presence of a base, okay? An ester or a triglyceride, for example, reacts to a base to form a soap and a glycerol. So take note when you are asked what is a saponification, that is um, hydrolysis in the presence of base. Okay. Then amides, as I said earlier, amides contain nitrogen bonded to a carbonyl group. These amides are encountered in the proteins. Okay, amino acids in proteins are linked together by amide bond. Okay, so these are examples of compounds that contain amide, acetaminophen, okay, and lysergic acid, a potent hallucinogen or LSD. This is the complex structure. You notice that there's a presence of an amide group.